the reason this lecture is a little bit longer than usual, so we spent some time here, but we spent quite a bit of time on tumor microenvironment because I want to tell you about three kinds of cells in a little bit more detail, okay? Because tumor microenvironment is a nightmare for oncologists, okay? That is so hard to treat, okay? So that is why let's see what exactly is going on in this tumor microenvironment, okay? So we obviously add VEGF inhibitors to inhibit angiogenesis, and we also target many other cells. So you have seen this picture, I won't go into detail. So it has a lot of different kinds of cells. It has hypoxic niche. These areas are hypoxic, so the cells which are surviving here, they are extremely aggressive, extremely aggressive. Every tumor in middle, usually if the tumor is big, in the middles, I don't know why, cells undergo necrosis. So recently I saw the PET scan of someone who had liver cancer, and the primary tumor inside, there was necrosis. This is like a feature of that, okay? Probably there is too much acidic, so those cells die here, okay? And then there is this acidic environment all around it, and PD-L1 is expressed and all of these things, okay? So these are not all the cells, but these are some of the immunosuppressive cells. So Bregs are B cells. We will not discuss that. We'll discuss these three cells. You know a little bit about TRAC cells, CTLA4, TAMs and MDSC. So these are huge culprits in promoting the tumors. Okay, MDSCs and TAMs, and these are all the good guys. Dendritic cells are APC cells, NK cells, CD8 and CD4 T cells. So let's start with MDSC cells. So these are myeloid-derived suppressor cells. And so what they do, they recruit TREG. TREG are also immunosuppressive. They inhibit T cells, they inhibit NK cells, they inhibit B cells, and they promote M2 macrophages. M2 macrophages are immunosuppressive. So you can guess anything they promote has to be immunosuppressive. Anything they inhibit has to be, immune promoting cells, okay? And tumor cells recruit MDSC and they also form MDSC. So it is like, they are recruiting people who are already polarized, and then they are changing the mind of those people also who are not polarized to become polarized, okay? So, so MDSC cells recruit TRAGs, recruit recruit TRAGs, recruit M2 macrophages, which are immunosuppressive, inhibit NK cells, inhibit NK cells. So you guys get the picture. This is the same thing here. So what do MDSC cells do? They create oxidative stress. So little bit of oxidative cells is very helpful to cancer cells, not too much. If you create too much oxidative stress, they will also die. So oxidative stress, they change the function of MSC. Antigen presentation doesn't occur, T cells cannot recognize them. Because these cells express PD-L1, you know what PD-L1 does. They secrete IL-10 and TGF-beta to make the tumor environment immunosuppressive, okay? This is, you already know, anti-PD-1, anti-CTL4, right? So MDSC suppress even when checkpoints are blocked. So even if you are doing, this is the part, MDSCs are so bad that even if you are doing CTL4 therapy and PD-1, PD-L1 therapy, even then the tumor environment will be so immunosuppressive, nothing will happen. Tumor will keep on growing. So they are that bad. So you have to kill MDSC cells independent of, in addition to PD-1, PD-L1 and CTLA4. So MDSCs also stimulate angiogenesis independently. They enhance tumor invasion and metastasis. They support cancer stem cells. They are central architects of tumor immune invasion, inflammation, metabolism, immune checkpoint suppression. You are just attacking PD-1, PD-L1. But look at MDSC, it is doing every single thing there. So even if you release the brake by doing PD-L1 therapy, MDSCs can still cut the engine. Okay, so this is really, really bad. So we have therapy against MDSC2. So there are ways to deplete MDSCs. These drugs will deplete MDSC. They will inhibit MDSC activity. They will inhibit the recruitment of MDSCs to the tumor sites, these drugs, and they will change MDSCs to another cell type, these drugs. So there are ways to deal with them also. Okay, now we come to TAM. TAM stands for tumor-associated macrophages. They also do a lot of bad things. They promote angiogenesis, tumor growth, migration, metastasis, inactivation of T cells, all the bad things. Okay, so TAMs are also equally bad, and they also do the immune checkpoint expression, immunosuppressive cytokines, metabolic suppression, crosstalk, bring in MDSCs, bring in TREGs. Okay, they also do all of those things. Okay, they promote angiogenesis, matrix remodeling, invasion, cancer, exactly like MDSCs. Okay, you can also target them. Okay, so there are many ways to destroy TAMs also. Okay, so we have ways of destroying TAMs also. Okay, so this is just the tumor. Now we come to TREG cells. You already know how bad are TREG cells with CTLA4, right? So these are MDSC cells, these are TAMs, all bad cells promoting cancer. So TREG cells, these are the ones which express CTLA4. Tumors actively recruit, expand, and stabilize TREGs, and then once they are really stable, they also promote angiogenesis. They're all bad guys, okay, recruited by the tumor cells. So mechanism of immune suppression, they inhibit APC maturation. TGA-beta suppresses T cells. CTLA4 you already know, okay, they also kill T cells directly. So they will spray perforin and granzyme, and perforin will make holes in T cells, granzyme will go inside, and they will kill it. Okay, so now we have seen the three really bad kind of immunosuppressive cells. Okay, so these are the TREG cells. It's the same picture here. Okay, so now there are different ways you can also target TREG cells. Okay, and once you target TREG cells, basically the immune system will become active again. Okay, so let's not go into the details of those things. So there are many ways to target the tumor microenvironment, but the point here is that now you understand how important it is to target the tumor microenvironment. Okay, so you can do immunotherapy, you can do radiation therapy. Oncolytic viruses are still here. They are the best guys, it seems. Okay, cell therapy, chemotherapy, targeted therapy. You know, I knew about the oncolytic virus for very long, and I was telling you guys for the past 1 week many different ways, but I got maximum questions about oncolytic virus. Okay, 101 also, and also in the class. Every person, you all saw potential in oncolytic virus, which I failed to see because I never got any feedback from anyone about oncolytic virus. But having said all of these things, I'm also wondering myself, it seems oncolytic virus seems the best one, because if you inhibit PD-1, PD-L1, it is just one thing out of so many things. Oncolytic virus is just cleaning up the whole mess there, right? And it will activate the immune system by bursting open the tumor there. So I don't know why it is not used so prevalently, or even if it is used, I'm just wondering if it is approved. I think it is approved, but let's check. Huh? Yeah, let's check. Okay, so now we come to the immune modulating small molecules. So I have just very few things here. I will just give you 2 examples. So you can add some small molecules which will make an immune suppressive environment more non-suppressive. So one of the ways is that, you know, the cold tumor basically is unresponsive to any therapy. So by turning on some signaling pathways, you can make it hot tumor. T cells will go inside, and then this can be killed. So there is a pathway called STING, stimulator of interferon genes. Okay, have you heard of STING pathway? So I had never heard of STING pathway myself. So there was a graduate student in my lab who worked in some other lab before she joined my lab, and she talked about STING pathway, and that was the first time I heard about STING word, because it never crossed my thing. So I'll tell you what is STING pathway. So it is a cytosolic immune sensing pathway that detects tumor DNA via C gas and triggers innate immune activation, leading to strong anti-tumor T responsible. So what happens is that usually when you do liquid biopsy, if there is a tumor anywhere in the body, some tumor cells will get lysed and release the DNA in the bloodstream. So if you check the blood, you will see this tumor DNA floating around. So there is this protein called C gas which will bind the tumor DNA. It's not like a receptor, it's like a signal transducer. So this will, when it sees this thing, this will turn on warning signal that this is a foreign DNA, and this STING pathway will be activated, and that will release interferon which will kill the tumor cells. That's as simple as that. Okay, so cytosolic DNA is sensed by C gas. You guys know adenylyl cyclase, many of you know, right? So there is a simplet cyclase which instead of forming cyclic AMP will form cyclic GMP. Okay, so cyclic GMP is formed, and this will activate STING. So DNA appears in cytosol, tumor DNA, viral or bacterial, and then C gas, which is cyclic GMP AMP synthase, detects DNA. C gas produces cyclic GMP, and then cyclic GMP binds STING. STING is activated, and it releases interferons, type 1 interferons, which will result in dendritic cell maturation, activation of T cells, increased antigen production. Immune cells will come, clean up the mess. Okay, that is STING pathway. Okay, so STING agonists restore innate. Why it is innate? Why not acquired? Say that again. Yeah, there is no antibody formation. It is always there. The moment it detects, it's instantaneous, right? It's an innate thing. Very good. It is an innate response. So solid tumors evade immunity by suppressing or down-regulating this pathway. Just imagine, cancer is something which happens in the body, and how smart are cancer cells to keep evading, keep evading, keep evading. This is it is almost unimaginable. Something which is foreign to our body comes in and then hijacks our own body for its own good. It's just surprising, because this is not coming from outside. This is our cells which are becoming cancerous, and then they fool our own body. It's just strange. So STING agonist activates STING pathway, which leads to T cell priming. So you guys understand. So more dendritic cells. What are dendritic cells again? They are APCs. So they present tumor antigens, so T cells will come, obviously, right? So one thing I did not highlight, I hope you guys picked up without my highlighting it. When MSC1 is activated, which kind of T cells come? Did you notice it? CD4. Yeah, helper cells are the one which come MSC1. MSC2 is CD8 cells. Okay. The CD8 T cells infiltrate the tumor, increase killing of cancer cells, improved response to checkpoint inhibitors, obviously. And they turn cold tumors into hot tumors. This is the STING activation, getting all the immune cells there. Okay. So now we come to TLR agonist, okay, immune modulating small molecules. So here this picture is very complicated, so let's look at this picture. So TLR is a receptor, toll-like receptor 9 agonist, stimulate innate and adaptive anti-tumor immune responses. Obviously that will work for tumor cells, right, if you activate both innate and adaptive. So TLR agonists bind TLR-9 receptors. This PDC, they are kind of DC cells, dendritic cells. They are called phosphodic or something D cells. They get activated, they release cytokine which will call NK cells. DC cells will mature. DC cells are dendritic cells, they present the antigen. If they present the antigen, B cells are going to secrete, antibodies. So that's why both innate and acquired response will occur. And the positive feedback loop and the response will keep on increasing. Yeah, this is plasmacytoid D cells. There are specific D cells. I don't know much about these cells, but these are the ones which are activated by TLR, and that activates both innate immunity and an adaptive immunity. Whenever dendritic cells are involved, you can imagine they are APC. They will present it, these helper cells will be activated, B cells will get activated, antibodies are going to be released. Okay. Now we come to something I'm hoping you are really waiting for this, CAR T therapy. How many of you are waiting for CAR T therapy? All of you. Yeah, this is a super exciting thing. This is something to overcome all the things tumor does. So tumor will remove MSC, they will hide it. So now we have something we don't even need MSC anymore with CAR T cell therapy. Okay. So CAR T cell therapy, the CAR T stands for chimeric antigen receptor T cell therapy. So T cells are removed from a patient genetically engineered to express CAR that targets a specific cancer antigen and then infused back to attack the tumor. So this is very, very, I think at least 1 or 2 or 3 or 4 are already approved for cancer. The only downside of CAR T cell therapy is that it is super expensive. Can you guess how much it costs a patient to undergo CAR T therapy? Huh? 60 lakhs. Sorry, you know what? I'm used to the difference. My mistake. Okay, I really cannot very quickly change it. My husband can, and he has lived in US longer, but for me, I just cannot change it very quickly. So
it's around 6,000 US dollars.
6,000 US dollars. It is $500,000 US dollars. 400K to 500K. So even the richest of the richest of the richest, I mean, like Bill Gates kind of people can do it. But the top 1% people can also not do $500,000 for a treatment. It is that expensive. Okay, it is that expensive. So it, it is very good for the people who can afford it. For us, it is better not to get cancer, right? Okay, so let's talk about what are these CAR T cells, okay, and then we'll talk about NK cells and other macrophages, T cells, macrophages, CAR next. Okay, so so they are extremely good for blood cancer. They also have some toxicity, but let's not go because they are extremely good guys. So what you know immunotherapy, I don't have to explain. Immunotherapy leverages the body's immune system to recognize tumor antigens. So CAR T therapy is a personalized adaptive cell therapy. Why it is personalized? Remember precision and personalized. Personalized is that individual person. So we go and see what exactly is the tumor, what is the specific antigen in that tumor, and then we make a receptor for that antigen, okay? And then we make a T cell. So we take the T cells out of the patient, then we put the DNA for that receptor there along with a lot of other things, and that receptor is expressed in that T cell, right? And when you give the T cells back to the patient, and then the T cells will go and bind there and they will kill the tumor cell. So that is what it is. So it is a personalized adaptive cell therapy. Patients' own T cells are genetically engineered to express CAR that recognizes specific tumor antigens independent of MSC. So tumor cells are down-regulating MSC. Now we don't even need MSC because we have just directly there. So activated CAR T cells bind antigen, kill tumor cells. Okay, this is like a living drug. So you remove the blood from patient to get T cells, make CAR T cells in the lab, insert the gene for whatever it has to bind, okay? Then you grow millions of cells, you take it back, and it will kill the cancer cells. Okay, so this is, you know, by antigen presenting this thing. So under normal circumstances, APC, these APC cells will present the antigen, and T cell receptor will recognize it, and once it recognizes it, it will be activated, right? But in T cells, they have this receptor here, which is designed in such a way that it will recognize the tumor antigen, and when it recognizes, it has other things to make it active, okay? And then it will release perforin and granzyme B, and it will create holes in it. Granzyme will go and it will kill the cells. It's like spray, like, you know, people keep spray to kill people, or at least stun them for some time, like a stun gun, right? Pepper spray, that's what I was thinking about, right? So this is worse than pepper spray. It kills the tumor cells, and we want to kill the tumor cells, right? We don't want to just stun them. Okay, that's what they do. So let's look at what is going on in here. What is this part here? Okay, in CAR T cells. So CAR T cell is a form of personalized cancer immunotherapy. So it targets and destroys cancer cells with high precision. You can understand, if you have to make CAR T for anything, it will take some time, because you have to get the antigen, then you have to really find the best antigen, right? And probably more than one antigen, because if you're just targeting one antigen, the tumor may just hide that one antigen after spending $500,000. So you have to probably make it, yeah, okay. To treat cancers that do not respond to standard therapy, okay. So, but approved CAR T therapies primarily treat blood leukemia, right? Leukemias are very hard and it's systemic, so CAR T therapies are very good. B cell lymphoma, mediastinal B cell lymphoma, mantle cell lymphoma, and multiple myeloma. Okay, so these form long-lasting remission. These are living drugs. So once you give it, it is just good for a long time. That's the good news. After infusion, CAR T cells can expand intensely in the patient body, persist for months to years. Okay, continually surveying and killing any cancer cells. So this is very good news for CAR T cell. They bypass tumor evasion. So tumors often downregulate MSC or inhibit natural T cell activation. Here it's a totally artificial machinery. So tumor cells cannot handle that. They cannot downregulate it. Okay. So it does not require, so tumors often downregulate. CARs bypass this because they do not require MSC presentation, directly activate T cells killing when antigen is recognized, and they can overcome these tumor suppressive signals. And this is highly personalized and highly targeted. So every CAR T cells are made from patient's own cell, autologous, reprogrammed individually in the lab and then reinfused. So CAR T therapy purpose is to engineer the patient's immune system to recognize, attack, and eliminate cancer cells with high specificity, especially when other treatments have failed. So this is not precision therapy. This is personalized therapy. Okay. Keep in mind, even if it is personalized today, it will become precision later on, because we will recognize how to use autologous cells and will make it, and then it will be affordable to most of the people. Go ahead.
Yeah, ma'am. I exactly wanted to ask about this affordability thing, because even though it's a good remedy, but then how do we mitigate the issue of like health disparity? Because that's what we were talking about like a lot of lectures ago. How do you make it available to the mass?
So there are, I think it is in one of my lectures, certainly it is in one of my lectures, how to not use patient's T cells, how to use a healthy donor's T cells. So we already know what are the things which immune system is looking for to recognize self versus foreign. So versus my T cells versus your T cells. So there are specific areas where our T cells are different. So our immune system will specifically look for those areas, and we know as scientists which are those areas. So what they do is that, suppose mind expresses some receptor. We all have some specific receptors which is unique to us. So if you downregulate those receptors in T cells, the immune system will not recognize one T cell from the other, right? So what they are doing now is they are taking T cells. So these are patients who have blood cancer, right, or leukemia. So they already have very poor T cell count, right? And then you're taking out T cells from their body, and then you're engineering it, and then you're expanding them. So it's like months therapy, and then you are injecting them back, right? So it would be great if you can take T cells from healthy patient and knock out those things which triggers the human immune system, which is already known, right? And then you make CAR T cell therapy and put it in the shelves, like in pharmacies or hospitals. And anytime a patient comes, it is ready to give. So that itself will cut down the cost, because it is not that person's T cells we are taking and individually doing it. We are doing it in bulk. Once you make T cells down-regulate, it's available to all, right? When immunotherapy came, it was super expensive, but now it is becoming affordable. It is still expensive, but it is becoming affordable.
Because in India, the thing is, people in West Bengal, there's a general trend that in West Bengal, a lot of people have leukemia. Like a lot of kids have that.
Yeah, the kids do have, I think you were asking me why kids develop leukemia, right? Yeah.
So if we can like make it mass available, it would be better for a country where they generally have less money. Like we cannot spend billions of dollars in that.
Of course, and even people who live in US, there is I don't know 0.0001% who can spend $500,000. Even if you are in the top 1%, $500,000 is nobody's. It is just really, I mean, yeah. Your life has to be worth living if you want to spend that much money. You better do something really awesome with that life. Okay. So, yeah, but the thing is this, that immunotherapy is affordable. You know that, right? I know people in India who are undergoing immunotherapy as we speak right now. Okay, like really close people I know. Okay, so immunotherapy is really affordable, which was considered really expensive. This is expensive, but it is not going to remain expensive, because ultimately the money will be made by spreading it all over the world. So whenever new things come, they are expensive, and then it becomes generic thing. So this will eventually become pretty affordable. So don't worry about it. This is just a start right now. And they are trying to go to off-the-shelf CAR T cell therapy. And once they get there, they are already there. So that will cut down the cost tremendously. And then, keep in mind, making CAR T therapy in US is more expensive than making it here, right? Because there you probably have to pay a lot. You have to pay in dollars to the people to do the work. Here you're paying in rupees, right? So it is just the difference in currency, right? I mean, India is a very expensive country also, not like old times. Because let's not get there, because we'll start a new discussion. But the thing is that if you do it in a different country than US, depending on which country, like for example, we get the same stuff from China a lot cheaper than if it is made in US, right? So if the Chinese, I don't know the market or anything, but if it is made in China, it will be a lot cheaper than when it is made in US, because they are going to charge more money than the people in China for whatever it is. So these drugs will become available in China for very, very, very low cost. To keep the market even, these people will also cut down the cost. So basically that's how the whole system evolves. So don't worry about that. It will become affordable to all someday. When something is fancy, new, it is very fancy, it is very expensive. But right now it is $500,000 cost for this one. Oh, there are, but patents are always broken, right? When Gleevec was done, I won't name the company because I'm on camera, but it was made here in no time, and it was sold here. So, and I have been to Mexico just for a trip, and all the prescription drugs in US, which you don't get it under doctor, it was just freely available at no cost in Mexico, right next to San Diego. So these things happen. So patent, yeah, okay. Sometimes it is good, sometimes it is not good. One should not break the patent because, legally it is not allowable, but whatever it is. Huh? Saving lives also matters, but again, one should not break the patent. Okay, to provide long-lasting remission, so I already told you, to bypass tumor evasion. So this is really, really awesome therapy, really awesome therapy. Now let's look at it, what exactly is going on. So this is the chimeric T cell receptor. It doesn't look like anything that we have seen in natural cells, I mean in regular cells. So this is the part which will recognize the antigen, okay. Then this is the hinge domain which will provide flexibility, okay. This is the transmembrane domain, and this yellow part is the one which will make it stable, and it will also do the cytokine release. So what if it just binds? Just binding is not enough, it has to release, spray the pepper spray, right? So that is the guy which will release the pepper spray, and this is the part which will activate the T cells, okay, so that it does all the spraying there, okay. So, so T cell activation requires, so I am just reminding you here, natural T cells, when APC cells present through MSC, they present the antigen TCR, T cell receptor binds the antigen and recognize it. Then you guys saw the B7-CD28, right? That is the second signal. But usually, so these two signals are there, then T cells will, then dendritic cells will release cytokines. This is the signal 3, which also will be recognized by T cells to get activated. So there are 3-tier activation, okay. So, and when they release the cytokines, the T cells which are bystander, they will also get attacked and they will also get activated. So there is a quick way of activating many T cells, and everybody does not have to lock horns with APC cells, okay. So the way this CAR works, that it has all of these domains, okay. Let's not go into the details of what is what, but just let's see how it works. So it tells you all the examples here. So this is the one which is equal to the antibody, which will recognize the antigen, and this is the co-stimulatory domain, and this is the activation domain. So here it tells you that this part here will make the receptor stable, okay, and this part activation is the one which will activate the T cells. So once it binds, it will activate the T cells, okay. So look at this structure here. So there are many variations of those things. So this is first generation CAR, second generation, third generation. See, we are adding more and more things. So they are becoming more and more effective, okay, without going into the details of that. Right now we are on the 5th generation CAR. I'm going to show you tomorrow real, like 10 different kinds of CAR. Like people have, it's becoming a toy where you attach this versus this versus this versus this, like 2 versus 3 versus 4. It's just a lot of fun to see what people have done, okay. So this is incorporate cytokine receptor animals, activate JAK-STAT signaling. They enhance proliferation of these cells, 4 generations required for universal cytokine killing. So don't worry about that, but what I'm saying is that we have highly advanced CAR T therapy now, okay. So this is first generation. It's just telling you different kinds of signaling domains which are added, okay, to make them even more powerful. So right now we are on the 5th generation. So CAR T manufacturing workflows, first you collect the patient's peripheral blood cells which are rich in T cell, then you isolate the T cells using anti-CD3, CD8 beads, then you add the viral vectors to express the CAR there, okay. You have to express CAR there, then you expand them, then you purify them, then you add it back, and then usually one-time infusion. In vivo proliferation peaks in first 2 weeks. I was in one of the students' thesis committee, and his lab was working on CAR T cells. But CAR T cells also get exhausted after a while. So they were working on how to keep them fresh so that they don't get exhausted. Okay. So, yeah.
What is this sleeping beauty transposons?
Transposons are one of the ways to get the gene inside there. So they go and they get integrated in the chromosome of the host. So this is just one way of doing it. Yeah. Have you worked with viral vectors? Anyone here has worked with viral vectors? No one has worked? Okay, in our lab we just only use viral vectors. We don't use transposons. But the beauty of viral vectors are that, have you, any of you done transfection in the lab? No transfection. So none of you have added DNA to mammalian cells. Okay, so when you want to express a protein in mammalian cells, right? So you buy lipofectamine, which is a commercially available transfection reagent, and you mix it with, and it will take DNA inside. But most of the cell will be transfected with an efficiency of 10 to 20%. But if you make a viral, if you package it in a virus, which we do all the time, I've been doing since my postdoc days. So if you package it in a virus, then the infection is 100%. So it expresses very, very nicely. Plus, it gets integrated in the chromosome of the cell. So it's there forever. Compared to DNA, if you add the DNA, it is there for some time, then it is, unless you select it. So it's a different story. So these are just a way to make stable cell lines so that the cells don't drop it off, right? Otherwise, you have to give selection pressure to keep it on. And human cells, you cannot give selection. You cannot keep on feeding drug, right? So that's why you use all these viral kind of systems there. So these are approved ones. Chiemria, Yescarta, Ticaratus. They are very strange names. I don't know how these names originated, but these are the ones, FDA approved CAR-T therapies for these diseases. So you can see that. And look at the response rate, complete response, 80 to 90%. It's fantastic response in refractory pediatric young adult. So it is pediatric, right? And then durable remission is 40 to 50%. In this one, 83%, superior to salvage chemo and autologous transplant. Multiple myeloma, 73 to 98%. So it's really effective. Durable means it remains, durable means it doesn't come back. It just maintains no cancer state. It's a durable response. It is not that it will be gone and that it comes back in no time. In cancer, that is the biggest problem. You don't want cancer to come back, right? It's a durable response. It stays there.
So it's after CAR-T therapy, it still comes back pain.
It doesn't. It comes in very few people. So it could be that the therapy was not properly administered, or there is something else wrong with that person, or the antigen is not the real antigen. It could be a couple of other things too, right? You have to choose the best antigen, right? So it overcomes immunosuppressive TME. It overcomes antigen. No, so challenges and limitations. So these are the challenges. It will answer your question. So you have to choose the right antigen, like it has to be really prevalent in the tumor, this thing. Sometimes immunosuppressive TME can be a problem even for CAR-T. Okay, poor trafficking, if it doesn't get there, then how will it work? It has to get there. Look at the cost here, right? It is really expensive. And then manufacturing failures there. You are working with human T cells, very few T cells. You have to really make sure that everything is working there. Okay, due to T cell, this is what I was telling you in that student's thesis, that T cells also get exhausted after a while. So they don't work. So a lot of research is going on to keep the T cells fresh, so that they are not exhausted.
No.
We have T and we get fresh, right? But we have to keep the T cells fresh also. Go ahead.
So is this therapy available here also in India?
I don't know. I really don't know. I am assuming that it should be available. It should definitely be available.
Ma'am, in India it is available. Immunoact. They developed IIT Bombay professor, Dr. Rahul Pawar.
He has developed it, yeah. So it is.
Approved also.
It is approved also?
Yes.
See, that is awesome.
If
Why not do it yourself? You can go for any other antigen and you can do it, right? Because this is if you have the protocol, you can develop it here. It is, I am thinking once you do it from healthy people and make it autologous, it's going to be much easier to administer. But I don't know what will be the cost in India, but it will be at least, no, not $500 million. It will not be $500 million here.
40 to 60 lakhs.
40 to 60 lakhs. How much?
60,000
60,000 USD.
Yeah, which is
Not
1/10 of this one. 60,000 is, affordable to many people here also and there also, right? But this is pretty expensive. All right, we are almost towards the end of this lecture. So this is just, you guys already know about immunotherapy resistance in cancer. We have been talking about it. So this is just listing a lot of things there. And that's the end of the story. Wow, we finished it. Wow, great. You guys are sticking with this, 4 lectures a week, which is 4 lectures a day, which is a lot.